Hi, everybody. I'm Olga Peters, and I have my co-conspirators here to present the tutorial, Doug Jacobson from Google, and Stephanie Brink from Livermore as well. We will be talking about Benchpark and Ramble today, basically for focusing on benchmarking. So let's see, the way, well, okay, so I guess maybe we can introduce ourselves really quick. I work at Livermore in the research arm of the computing. My focus has been performance tools, application performance on our high performance architectures, which of course includes benchmarking. Doug, would you like to introduce yourself?
Sure. I'm at Google. I work on the HPC workload performance team, where we focus on optimizing the performance of a variety of workloads, whether they're benchmarks or customer workloads that need to have better performance. And that is what led me to work on Ramble.
All right, thank you. All right, so our agenda is going to be close to the following. Introductions. We will start talking about Benchpark, which is the software we have at Livermore that builds on Ramble for benchmarking. We'll have a hands-on portion. So for that, I will talk in a minute about how to get to AWS instances we have set up for that. Then we'll talk about Ramble overview and some basic instructions. And then we will have another hands-on using Benchpark basically to do another experiment, to add an experiment in Benchpark. And so basically, we do want to have this interactive. Essentially, you'll have to post a question in chat, and whoever's not speaking out of us co-hosts, please interrupt the speaking person because we cannot see the chat. At least I cannot. So please interrupt and read off the question. There's more teammates on the line, and so of course they're able to also answer answer questions directly in chat if appropriate. So yes, welcome. Let's see. So tutorial materials are posted here. So softwarelnl.gov/benchpark is where the benchpark documentation is. And so we will be following the first hands-on will be following the basic tutorial on the HTML. We do have a Slack channel. It's part of the SPAC Slack, which I'll talk about in a minute why that is. But basically, there is a Benchpark support channel that everybody is welcome to join if you're going to be playing with Benchpark and have any questions at all. Let us know. And basically, this will give you an avenue to interact with the team after the tutorial has ended. Let's see. Okay. So the Amazon instance that we have set up for the tutorial is here, or you can also go to this QR code. So we have the instance for the hands-on component of the tutorial. It's got Benchpark installed in it and required dependencies. It does have a job scheduler so that you can submit your jobs as if as you would on any HPC cluster. So when you're logging into the instance, please use a unique username to avoid resource allocation conflicts. This is a shared cluster. First initial followed by last name should work. Hopefully, we shouldn't have conflicts that way. And the password is HPC tutorial 25. We encourage you to go ahead and try that now. The reason for this is it's actually been taking us a couple of times to log in. We hypothesize that it has to do with the speed with which you type the password. So don't be alarmed if it doesn't let you log in the first time. Try a couple of times more. Eventually, it should let you just log in. We do not know why this happens. So apologies for that. Just try a couple more times, and then hopefully that works for you. So hopefully at this point, you guys are trying to log in. Are folks able to log in? If you're able to log in, please post a yes or something for us in the chat.
Yeah, some people are able to log in.
Okay, if anybody's having trouble, again, try a handful of times first, but if anybody's having trouble, please let us know also in the chat. All right, okay, and so we'll jump into the tutorial. It's almost 10 after. Let's get started. So the reason you guys are on this tutorial is probably because you do one of the things on the list here. We benchmark HPC systems for many reasons. We benchmark them to procure machines such as El Capitan. We tell the vendors what our workloads are like and co-design systems with them. We also get early hardware and we try to benchmark it and see, if it's approaching the performance that we're expecting out of the full machine. We also do it as a part of contractual specification for system acceptance. And of course, along the way, we do all the things with those benchmarks, right? Those are often the first things to be built on the machine, the first things to be debugged, their correctness tools, tests. We use performance tools to understand the performance. And of course, a lot of us do research using benchmarks in both for programming models, different computational methods, or across different hardware architectures. So many reasons to do this. If you are willing to put a reason that you are in this tutorial in the chat, that would be fantastic, and we could look through that. Okay. So the challenge, of course, is that this is not a simple thing to do. So here I'm showing a top 500 lab pack results basically that have gone back to the 90s, right? This is one data point, or well, rather one data point over time, right? It characterizes a very specific thing. It characterizes dense matrix computation. But depending on what it is that you do for workload with your machine, um, that may not be the best. That may not be an accurate representation of what you're trying to characterize. And so there's a lot of work that goes into developing these benchmarks to represent our workloads. We're always asking questions. Are we capturing the best the system can do? Is there something else going on that's impacting your performance, like OS noise or traffic on the network? Right, there's a lot of things that we, as we benchmark, we try to figure out why the performance looks a certain way. And then, of course, building and running the code correctly or in an optimal way or a producible way, right? So those are another challenges of benchmarking. And the reason this is so challenging is because we now have a proliferation of very diverse HPC hardware. The benchmark source code then tries to adjust to it, right? We can try to write some portable abstraction layers into our benchmarks, such as OpenMP, Raja, or Cocos. To be able to target the AMD GPUs, the Power 9s, or the NVIDIA GPUs, Intel GPUs, the ARMs on Fujitsu, etc. This in itself is a challenge. And so a lot of the native way to write code is going to be very hardware specific, and so we tend to sometimes we have to do that, and sometimes we try to have a portability layer that enables us to use the same benchmark on different architectures. Of course, because it's all about performance, we are optimizing all of this code, right? We try to take the most effective use of the hardware, and that can make orders of magnitude difference in performance on how you're building and running your benchmarks or your applications. We also rely heavily on system packages, right? All of these systems that I am showing here on the left have pretty specialized interconnects, and they also have very specialized and optimized for that specific system MPI libraries that you will want to use with your on this machine. You will not want to just build necessarily a regular MPI that doesn't know all of the details of the interconnect and how to best leverage it. So we rely heavily on system packages. And so as a result, writing the source code is only the beginning, right? There's a lot more work that goes in after that, right? The current state of the art is that basically the system benchmarking is very manual. And so a lot of us are spending a lot of time building benchmarks on different systems, trying to port to new systems, trying to, go to a new trying to go to the new version of the hardware or a different vendor's hardware. Running on all the systems is different. Sometimes, there's different launchers, different schedulers. Porting the run scripts to new systems is also manual and tedious at the moment. And also our systems keep changing, right? We keep getting new ones because, with every new generation, there's new architectures that are coming up. There's faster compute that's coming down the line that we want to leverage. And so keeping things building and running is actually quite a challenge. And even triggering these builds is often manual. It takes a human to do many steps of this process in order to even get to collecting the results. And then you're going to be analyzing those results. And again, that's often a manual process. So essentially, where we started was this journey is basically saying, all right, HPC benchmarks are HPC software. There's no difference. They're usually just smaller than our applications, right? And so we have to take all of the same considerations with the benchmarks as we do with the rest of our software. We have to think about portability for the source code, maintainability of the source code. We need to think about, building, testing, verifying the results. We need to be able to scale up the benchmarks to bigger machines. We need to be able to reproduce them. And all of these components must work for your specific system. And so the focus always is on explainable performance. And so what we started with Benchpark, the goal has been to have a complete specification of HPC benchmarks. Essentially, you can think of this as an infrastructure as code specification, where we codify the build and the run instructions, and also the HPC systems we are working on, the specific experiments we are running. And of course, for all of that, we will be leveraging the HPC automation that exists, right? So source code on GitHub is easiest, although private repos are also possible. Build specifications, we're using SPAC since there's been a lot of investment into specifying builds in this way. Also run specification, that comes from Ramble to us, which you will hear about in a little bit from Doug. And essentially, once you have codified everything, you can actually leverage CI for running this, right? Once every step of the process there is codified, then you no longer need to follow some README file, right? A computer can run it the same way a human can run it. So that's been the goal. Every part of the specification is codified. That way we can use that specification to communicate our workloads with others, whether it's internally in the same organization or externally. And we can also use this for automation. All right, and so basically the idea is if you have specified how to build and run your benchmarks on a specific system, you should be able to run on that system. You should be able to rerun on that system, whether you are the same user on the system or your colleague on the same system, right? Taking that specification should enable both of you to run the same way. You should be able to replicate an experiment on a new system. So if you're able to run on this new system, you should be able to run the same experiment on the new system and compare performance, for example. You should be able to maintain your specification, so the benchmark source and all of the specification that goes with it. That way, you can put it in CI and essentially know when it's when it's breaking, right? So you can attend to it, and you can also record everything. So this specification becomes a record, the full specification of the experiment, what all went on, what system were you on, what software stack you used exactly, and how exactly what and how exactly you ran on this, right? And so this full specification enables reproducibility, replicability, and automation. I don't know why I have an assistant. Okay. Are there any questions so far in the chat?
No, we're just working through issues on the login.
Okay. Does it all seem solvable so far?
Yeah.
Okay,
Yep.
good. All right, appreciate that. Okay, so what do I mean by specifying an HPC system? Basically, we want to specify the resources, how many CPU cores on a node, how many GPUs on a node, what scheduler your system is using, whether it's Slurm or Flux, how are you going to map processes to cores, to sockets, to GPUs, and to hopefully even to your NICs in the future. We don't quite do that yet. How you can explore what kind of one-node parallelism you can have, whether you need CUDA to program it, ROCm to program it, OpenMP, what have you. And last but not least, the software stack on your system. Which compilers do you have available? Which of them is the recommended one? You can compare compilers as well, right? That can be part of your experimentation. But you need to know which ones are available. You also need to know which implementations, which MPI implementations are best, on your system. And you could indeed build your own as well and compare that with the system installed one just to see if, what benefits you're getting from that. Also, math libraries are often highly optimized. Again, if you want to use those, you should know which ones are available on your system, and or you can build them yourself if you choose to. But the whole point is to define the system for performance, right? We are trying to define all the things so that you know everything about the system in order to get the best performance out of it. And so the way that looks like in Benchpark, it's a Python class. It's going to tell you, you're going to have some options, right? You're going to say, all right, so El Capitan uses ROCm for the on-node parallelization. There's a handful of versions available, right? There is, and then the default one that the sysadmins are currently recommending that you use is, let's say, one of them, right? And so you're going to be able to select which ROCm you want to use, or if you're not wanting to select, you can just use a default one. Same thing for the compiler, right? There is GCC, CCE, ROCm CCE on the system. Let's say the default is CCE. You can set, the system scheduler and then the resources and so on. So this is a small piece of the Benchpark El Capitan specification. By the way, in Benchpark, if you just go into systems, you will see all these directories for all these different systems that we have. Again, this is a truncated list. And as you will see in the hands-on shortly, well, we won't be running on El Capitan. We'll be running on AWS parallel cluster. But essentially, once that system is specified, a file like this exists, Then you can initialize that system, right? You can basically say, all right, I'm gonna want to use El Capitan. Oh, by the way, I will want to choose the newer ROCm version just because that's what I want to do today. I will want to choose a compiler. Since this is the default, you don't have to specify it, but you can. But all of this is getting recorded as you specify your system. Let's see. So any questions so far?
Nope.
All right. So if you go to the Benchpark docs, there's a catalog there, and there's system specifications in here, right? And you can see what types of systems there are, which vendors. Um, this is a screenshot, but if you scroll to the right, you'll see where the systems are cited and which ones have been tested. For example, right, there is many of the Zen 3 MI250X systems around the world at the moment, and so there's several, right, that this specification can work for, as long as they have the same hardware and the same software stack specification. There's also a benchmarks and experiments catalog, which I will get to in a moment. Okay, and so as of last month, we had, or 2 months ago, I guess, we had quite a few systems specified in Benchpark, 4 in Europe, 6 in the US labs, 1 in Japan, 1 from at a university, and 2 cloud systems. Basically, if you are planning to run on one of these systems that are already specified, that's already done for you. So you can just use that specification and you don't need to write one. If you do need to write one, that basically you would be then looking for an example among here. Probably there's instructions on in the documentation on how to do that. Okay. So similarly, we have HPC experiment definitions, right? So that's going to specify what kind of source code do you have? What does this work with? Does this work with CUDA system, CUDA runtime, ROCm runtime, OpenMP runtime? What's the problem size? How many resources do you need? Do you care about the number of nodes, number of cores, or number of GPUs for your workload? You can also do scaling studies. You can specify how to strong scale, weak scale, how to decompose your problem. And as I already said, how do you map your problem size to the resources? And so the goal here is to have a reproducible set of experiments that map onto specific systems, right? So you're going to say, all right, I have ROCm and these are the problem sizes. And you're going to have that experiment.py specify your problem, and then you're going to be able to hand it over to a colleague and run on the same machine or another machine that has ROCm as well. Okay, so the experiment example here, we will actually write one. So we'll write one in the second hands-on, but you can see the ones that are specified in Benchpark already. So we have AMG, which is basically an experiment, algebraic multigrid using the Hyper library. It's possible to run it with OpenMP. It's possible to run it with CUDA. It's possible to run it with ROCm. We have defined the strong scaling and weak scaling for it, and a throughput scaling. And we've also instrumented AMG with caliper. So I'll talk about that in a little bit. This is for measuring performance kind of in detail. Where do you spend your time? Is it in MPI? Is it in the solver? Where does the time go? We've provided a couple of workloads, right? So there is 2 problems in there, and you can choose which one to execute. Of course, you'll always get a default if you don't specify. And here's a little bit of code. We will dive into that when we are adding an experiment towards the end of this tutorial. But basically, you're going to specify how to map your resources and problem sizes so that you can have the strong and weak scaling and throughput scaling. All right, and so the way you would initialize, once this class is written, the way you would initialize your experiment is you would say benchmark experiment init. You would provide where to store it. You would say we want ROCm, the ROCm version. We want the strong scaling. We do want problem 2. And yes, we do want measurements. We care about MPI and time. And then you'll also say, okay, and I'm initializing for some system like El Capitan, some system that has ROCm. So something with AMD GPUs. Okay, and so as I mentioned already, there is a catalog here of what exists, and so you can scroll through and see which benchmarks are already represented. And we did attempt to make put in a bit of information in here of what the benchmarks do. Are they large scale? Do they use MPI? Do they have collectives, point to points? Do they use any math libraries, solvers, etc.? What language they're in, and so on. So there's a bit of a metadata that gets generated into this table. By the way, this information is inside of the experiment itself, right? But this table is generated from that specification, but just kind of as a summary for all of you. Okay, and so as of July, we had the following experiments, right? We've got HPL, HPCG, a couple of micro benchmarks like the MPI benchmarks and IOR. And we do have a handful of, well, mostly we have benchmarks from the US at this point. We do have some contributions from Europe. This one's not a benchmark. This one's a full-blown application, actually, GROMACS. And we have 2 benchmarks at the moment that Riken in Japan contributed, because they're also using this to run their benchmarks on their Fugaku machine. Okay, and so once you have run everything, and we'll get to this in the first demonstration, there is going to be a command that's going to let you analyze your results, right? And so if you've defined strong scaling, right, and you've run some strong scaling study from 4 to 32 ranks here, as in this example, everything is recorded, right? You have full information of what happened, the total problem size. We're going to be, if this benchmark is instrumented with caliper, we're going to show you how the time is split between these functions. You can see the call tree where the functions are being called, and there is a fair bit more options that you can see basically in this benchmark analyze docs here. We're using caliper for measurement, and we're using a library that also comes out of Livermore, Thicket for the analysis of the multiple runs. Okay, so we have a fair bit of contributors from kind of around the world. Obviously, we started this at Livermore, so a handful of folks at Livermore are contributing, but we do have contributors from other labs that are interested in this software, and some of them are using it more than others. Let's just put it that way. So currently 60% of the contributors are not from Livermore. They're from 10 other organizations. If you look at the GitHub page on the front, there's some handy widgets there, and basically you can navigate to see what CI we are running on CDash. There's also being posted on CDash, and it will tell you what we're testing. on which machine, what's passing. I see a fail here, right? When it ran and so on. So this can be kind of handy to see what's up to date, what is working on which machines, and it's our goal to basically maintain it, right? And you know, so if we care to fix script key, right, we want to make sure we figure out, we'll go to the logs of this and see what's broken and go work on fixing this so that we have green across the board. So this is where our CI tests are posted. If other centers want to post their results, if they start running stuff in CI, we would welcome that as well. That would be very interesting to see who's running what and what's being successful and so on. Okay, and so as you will see in a tutorial in a moment, we codify benchmarking steps, right? You'd clone Benchpark, which you don't need to do for the tutorial because we've set it up for you in the instance. You can list which systems are described, right? And you can pick out of the available ones, or you need to add your own. You can list what experiments are specified. You can pick an existing one. You can again, choose to add a new one, as we will in a second in the last portion of this tutorial. And then you basically run the commands for setting up the workspace. At this point, actually, we're handing the workflow over to Ramble, which Doug will describe in a bit. Basically, Ramble is what sets up its own workspace. Ramble is what calls SPAC to actually build the code, and it will take the specification from Benchpark, and it will generate full specification for running from that as well. And when you type Ramble on, this is how you submit the experiment to your system through whichever queuing system it's got and so on. And then basically you can see when things are completed, and then you can do analysis after that. And so essentially, we're not replacing the benchmark source. That's still, on GitHub, preferably, as always. We can work with starballs, but it's kind of hard, a little harder. We don't replace the build system, right? Basically, if this is a CMake package, if this is a CMake benchmark, and it has a spec package, right? We just use those. We do not replace that. Nor do we replace how Doug has specified the Ramble instructions on how to run, right? We are building on all of that, and we are adding system descriptions, system specifications for compilers, MPI, and math libraries, and we're adding experiments and how they map onto these systems. And so this is a tad abbreviated, maybe. You'll see in a moment what this really looks like. But essentially, if the system you're wanting to run on is already specified, if the benchmark you're wanting to run is also already specified, you can just get going with just a few commands. There is no code to swap. There is no readmes to follow, right? Everything is codified. These are the instructions that you are using to get going. Okay, and so essentially, the hope is we're doing this. A lot of people do benchmarking, right? So the hope is that we make it easier for end users to run HPC benchmarks, right? So if you're running AMG and I am running AMG, we could specify it one time and share amongst ourselves that specification so that we can both run and maintain it as in collaboratively. And we can all analyze the performance of these benchmarks. It's also for benchmark developers. So if you want to share your benchmark, if you provide it in a way that's easy for people to try, instead of investing hours to figure out how to build it, and how to run it, right? If all of that is codified for them in a way that's easy for them to take, hopefully they would be more inclined to try out your benchmark. Of course, part of the reason this project was started is for procurement teams at Livermore, because we want to curate the workload representation and evaluate and monitor system progress. I am quite certain that a lot of the HPC centers essentially do very similar things. And so hopefully we can share the specifications that we already have and actually kind of have a common process to do that and help each other out. And it's also for HPC vendors, right? A lot of times when the vendors come online and they try to work with HPC centers to provide us hardware, they are trying to understand our workloads. They are trying to run those benchmarks to kind of as a proxy for our workload, right? That's what we provided. So again, they are doing all of these steps and all of this benchmarking in order to understand the benchmarks on the current hardware and in order to propose the future systems that would alleviate some performance bottlenecks or improve performance of these benchmarks. And so the end result, hopefully, is a catalog library of benchmarks that are working, right? So the C- exists there for a reason. You can see what's working and what's not. And so a library of working benchmarks can enable architectural explorations, explorations of the software stack, comparing which compilers are better, which MPIs are better, um, and also over time, right? If your system is on the floor for 7 years, is it slowing down, right? There's a lot of experimentation you can do. Um, your software stack can march on forward as you increase your raw conversions. Are you getting the same performance or better performance? Nobody complains about better performance. People do complain about worse performance, right? So this will take you, this will tell you if you're running CI consistently, you can see over time what that's looking like, and correlate that with your raw conversions and so on. So you can ask a lot of questions, you know, which architecture and system configuration is best for your benchmark. You know, I built OpenMPI out of the box. Is that as good as the MPI that's provided on the system? Um, and you know, a lot of other questions like that. You know, before you guys leave here today, I hope you leave us with some thoughts of what you might be wanting to address with Benchmark. But overall, right, we're trying to build a community that can contribute and benefit from the work that the community as a whole is doing. We want to curate benchmarks. We want to collaborate on this work, and we want to do research as part of our daily jobs, right? Okay. And so basically, it's an open collaborative repository for reproducible specification of HPC benchmarks, right? I mentioned it's infrastructure as code. We are codified HPC systems and HPC experiments. You should be able to do all of these things with it. In addition, right, there's tagging, keywords for publication. It would be excellent to submit a full specification of what you ran along with your publication, right, for reproducibility. What performance metrics you were using, what do you find useful, right? What are people doing with now that things are working and running? And being measured, right? You can have dashboards where we can archive specifications and results together so that you don't get a data point with no explanation of where it came from. You can have pipelines across data centers and across the world and in the cloud. Basically, you know, this enables a lot of collaboration, and that's what we would like to see um, drive our community forward. So there is a handful of papers that we have tried to write. So there was an early paper that came out at SC23 in the HPC test workshop. And just in July, we had a publication in ACM reproducibility conference to kind of talk about the reproducibility aspect of what we're doing. All right, so our future directions, right? We are curating a suite. We're looking for a reproducible specification of an entire suite. We want to be doing tagging so that it's easier for a human to navigate things and find benchmarks, right? If you're looking for benchmarks that will run on your system with CUDA, you should be able to do that. So that already exists in Benchpark. There's different metrics of usefulness that we want to explore, dashboards, results. We can have any slice in the configuration space. Once we have a large configuration space, that it's nice to be able to take a look at what you're interested in. CI pipelines. We want to have a community engagement, co-design with vendors, application teams. There's always a discussion of like, how do we encourage folks? So if anyone has ideas or you know what's encouraging you, again, we're interested to hear. There's questions that we are yet to fully address, right? We don't know who owns which part of the specification. Some of that is easy, right? So El Capitan is a Livermore machine. Livermore should own the specification of El Capitan and probably approve changes. But then if there are truly shared specifications or benchmarks, you know, that might take a different kind of consensus to approve changes and so on. You know, other questions are who finances R&D and maintenance. The hope is that the open source community, if we have enough engaged folks, that helps. But you know, it doesn't hurt to ask this question and see if we can formally have some funding for the project at some point in time. And what's the return on investment for the people working on it, right? Hopefully, if you've gotten something to work, right, you have that specification. Hopefully, you can share it. But you know, the end result is that if you do share it and there's postdocs, researchers, graduate students, vendors, everybody who can now leverage that piece, you know, they'll contribute something else and you might be able to leverage that. And so, you know, a lot of collaboration is possible as a result here. So basically, I've got my Amazon instance on the left here, and I've got the tutorial on the right. Or anybody need help
Yes, we can see.
getting there? Okay, we're good. So basically, we can go here and we can essentially start going through. So the instructions here are in yellow, so you can just basically go along with me. Right, this will tell you that we're at 0.1.0. Let's see. Okay, and so this is telling you in red is the benchmark, right? In blue are the programming models it's currently working with. And if somebody has implemented scaling, that would be reflected here as well. So AMG that we looked at a moment ago, right? We have all these options for it here. And so you can basically look for what you're interested in. You can look for specific, let's say you want to look for Kripke, right? You can see for specific instructions that are available. You can also say, all right, let me see which, you know, this is a lot of information, but let me see what benchmarks are available to run on my CUDA machine. Okay, and so here's the trimmed up list, right? So some of these where are not do not have a CUDA version. This is not quite. We need to work on providing another option because, for example, well, not Stream. For Stream, you would need a separate version to run in CUDA, but for MPI experiments, right, you could run this on your CUDA machine. It just means that right now you would be just running on the CPUs. Nobody's yet implemented a way to use GPU-aware GPU-aware version of this benchmark, right? But technically that can be added, right? Just like for the Stream version, you would need to add source code as well, which we are working on. Actually, Babel Stream is our CUDA version of Stream, and there is a ROCm version of it as well. Okay. So when you have decided what it is that you want to do, you can also say systems, right? And so today, this first demo is to go into basically using the AWS tutorial benchmark. This is not big enough. Let me see. Okay, better. All right, and so you'll have to go into Benchpark. Or are we already in Benchpark? Nope. And basically initialize that system. Okay, and we're done. So it's setting up a number of files for you that you can go poke around to see what's being generated there. This is actually information that gets passed on to Ramble later on. Some of this is for setting up the the information about which scheduler the system has and so on. And some of this is about the software stack that Ramble will in turn pass on to SPAC to build your benchmark when you're ready. Okay, and so let's initialize an experiment. And so we're initializing it specifically for the system that we just initialized. What else did I have here? Okay, and we want to measure it. So this one is instrumented with Caliper. So we can
Hey,
just,
Olga,
yes.
there's a request to make your terminal font bigger.
Does that work? I don't think that's working. No. No. Okay. Oh, okay. That works, but can I close this? Shrink it. Can I close it?
Yeah, I think if you click the folder on the far left,
This
to
one?
the left of the
Oh,
plus.
okay. All right. Is this better? Okay, that better? Or do I need to go
It
back?
looks bigger to me. We'll see if people want it bigger still, but I'll let you know.
Okay. Let's see. Okay, thank you. HPC tutorial. So as I was saying, we want to use the system that we just initialized. And we are going to do a strong scaling study today. And since we have instrumented this benchmark with Caliper, we can also enable timing. which will let us look at the timing results when we're done here. Okay, so what is this doing? It's generating more information to pass on to Ramble for how to run this specific, how to run and build this specific experiment for this specific system. And so the next step is Benchpark setup. And so you're going to need a workspace to where everything is going to be generated, built, etc. So that's what we're doing.
And Olga, while this is going, I guess maybe get to the Ramble setup.
Yeah.
But we do have a question in the chat once we kind of get to a step where things take a little bit.
Okay, so basically this spits out the instructions to you. So essentially you want to run the setup.sh. That one's fast. So this instructions here as well, and if you missed it in your terminal, but let me type up this command. Actually, well, I don't want to do that. Let me type up this command, and that's the one that's going to take a while. So while everybody's waiting for that, I will answer the question. Oh, this is not letting me tab.
You have a B instead of a V in Joyvion.
That's why that doesn't exist. Maybe it will let me type now. Oh, yes, better. Workspace. So, okay. Sorry, too far. So just to be clear, this is a Ramble command, right? We're giving it parameters, but this is a Ramble workspace setup. And once you get through that, this is what's actually going to be building and generating the job submission scripts for your benchmark, for your experiment. All right, Stephanie, what was the question?
And so the question was, is Benchpark being used on LCAP and other Livermore systems? Why is Benchpark preferred over other tools that exist out there?
So, okay, so let's see. We have used a myriad of tools over the years. There's some limitations and some basically technology choices preferences that are baked into this. Essentially, Livermore is a spec shop, so a spec-based system makes a lot more sense to us. When we started out, a lot of the systems were not working with spec, right? Ramble was, which Doug will explain in a few minutes once we're done with this demo. So that was kind of a starting point for that. That was one of the reasons. Another reason was we wanted to tightly control that we are using the system software that's on the system, that we're able to compare the different versions on the system. Again, that was not necessarily simple in other systems. Essentially, this is a culmination of many years of doing it other ways, if that helps. Is there a follow-on question to that by chance?
Nope, I think you answered it. Thank you.
Yep. So basically, this is coming out of the team that has been doing benchmarking on LCAP for El Capitan acceptance, and we've learned from our experience. Okay, so once you get to this point, this is basically completed generating all of these files that it's outputting. You can go take a look, but it's essentially generating your So it's built your experiment, it's built your binaries, and it's generated the job submission scripts to just run it. And so this next step, Ramble on command, will submit it to running. So let's get through that. Okay. Workspace. And that's it. I don't believe there's anything else. Yeah. And so basically, Ramble on is the command, and we just gave it the directory where we've just set up all of these results. And so now, what it has done is it's submitted the jobs on using Flux actually. The funny looking F here is giving that away, but this is basically we set up this instance to have a mini Flux version for all of you, and so this has submitted these jobs to that scheduler, and you know, basically they're short. These are short jobs, so they should be running really quickly here. And so you can query, you know, whether they have run. Yeah, so this one's running, right? And so you will, it will take a minute to finish running, because of how we set it up. We didn't spin up a ton of resources, right? So this is these next ones can't run until this one finishes, right? Okay, so maybe we're good to go. Let's see. And so basically, once you're at this point that all of your jobs have completed, you can start analyzing the results. And so what we've queued up is basically a simple analysis step. As I said, benchmark analyze, you can find it. Yeah, well, there is here. This menu option, there is more options that are available to you there. But for this tutorial, we're just going with this one command here. Again, you have to give it the workspace. Let's see. Let's say we just want to look at the results without MPI, just the compute functions. So we can subtract out the MPI. Sometimes that's useful because there's going to be a lot of calls and maybe you don't want to see how long they're taking. But you can basically the script lets you use different subsets of data however you need, and you can even do a little bit of a specification on how it looks. The tool that's behind this is a Python tool, and basically if you dive into the Python tool itself, all the options are available for you there. But this, as part of Benchpark, oh, that didn't work. What did I do wrong?
Someone spotted a typo in your workspace stir. Oh, your flag itself is missing a K for benchmark analyze.
Yeah, okay.
Nice
There it
catch.
is. Let's do it again. Okay, so at this point, I'm gonna want my files back. Do I? Yeah. So, so these files that you're looking at here are. Did we decide that we know how to type this in, or do I need to click through?
We did find a way to do it, but you can also be clicking through. But basically, the way to do it is, I think it was file open from path. The top
There it is.
open from
Yeah.
path. And I
Okay.
think I think it's we decided it is relative, so I think you take off the I think it was start at workspace and forward.
Mhm. Okay.
Oh, start with Benchpark, sorry. So you can do Benchpark / workspace.
Okay. Let me see if I can copy this in here. All right, and so you see these files here. So this is going to be, well, no, this is big. But this basically this this figure here, they are all going to be a little different, right? So these did indeed run. So each of you just ran it. You know, there might be a little noise. They're not going to be identical numbers here that you're getting. Like this picture shows under 25 seconds. This one's a little longer, right? For whatever reason. But you can essentially see the proportion of the time that you are spending in all these different calls. You can see this call tree, right? You can see where those functions are in the call tree, and you can see the ranges of their values. And you can also just get at the data that you can grab either in Python or whichever way you want, and actually do your own figures if you'd like. But basically, this outputs the experiment data that you have gathered, right? And so these are, you know, basically the measurements that you had for these different runs, right? So this is the run on 4 ranks, 8 ranks, 16, 32, and essentially the times that were measured in those functions that are not expanded here. Yeah, so this is main, but there's all the other functions here as well, if you're interested, right, that were measured. And you can basically see the scalability for all of them, or whatever experiment you're doing here, whatever you're interested in here. So let's see, any questions here?
No, I haven't seen any yet.
All right, and so basically, you know, this is, if you're interested in running a specified experiment on a system that's been specified, that this is all it really took you to get to essentially looking at the data already, measuring. You know, you might then want to scale up higher or what have you, but essentially, you know, this gets you going very quickly. Hopefully that part is very clear.
I'm Doug. I'm going to talk to you about Ramble now. I won't have access to the chat while I'm doing this, similarly to how Olga did a bit ago. Okay, so this section is just all about what is Ramble. I'm going to talk a little bit about what Ramble is and some of the workflow and some of the things that you can do with it, just so that you have an understanding of some of the things that you did in that first hands-on. Let's do this. There we go. Okay, so Ramble is something that we've talked about a lot in this, but it is an open source experimentation framework that's written in Python. It has a lot of goals. I'm not going to go through these. It's basically make your life better when you're benchmarking stuff or running a large set of experiments. At the bottom, you can see what my thoughts are on it. It's really good at generating parameterized experiments. It doesn't have to be just benchmarking. You could use it for science if you wanted to. You can do scientific parameter studies with it pretty easily, in addition to it being useful for benchmarking and looking at performance of various experiments. I think that kind of gives a little bit of my answer to Olga's question earlier, which was, is it better to use a carrot or a stick? I feel like like a lot of the thoughts that I put into Ramble were driven by trying to make it something that's useful for me to do benchmarking and performance studies, but also for scientists to use, because I feel like the more useful it is for them, the more likely it is to get benchmarks or things that I could use for benchmarking added into it in the future by those people, and then maintain it easier. So I already mentioned this, but Ramble is written in Python. We've used it on a bunch of platforms. It's heavily based on SPAC, just so you all know. It uses SPAC's infrastructure under the hood. It has a command interface that's very similar to SPAC's. It's an experimentation framework, like I said. It's like running experiments. It is to running experiments like SPAC is to building software. It's on GitHub, and it's good at parameterizing stuff. And it has a domain-specific language, which is also part of some of the infrastructure that we inherited from SPAC, how we define applications and experiments and package managers and stuff as well. This is a bit about the high-level architecture of Ramble, just to give you a mental model. Ramble's in the middle here. There are inputs on the left and then outputs on the right. On the left, there is a software stack configuration in the top in that bubble. This is provided usually by something like SPAC or Easy or whatever you want the package manager to be. There are application definitions. There are also other definitions, but probably the most important ones for creating experiments are application definitions right now. Each application has its own application definition, which is very similar to a package definition in SPAC. It's written in Python, it's a class, it represents a lot of the building blocks that you need to take that application and create experiments from it. And then in the bottom, in the green, there's an experiment configuration file. This is in YAML. It's similar to a SPAC environment file, but it describes things differently, or it describes completely different things. It's the primary interface that users interact with Ramble in. It's how you configure the experiments you want to run, how you describe the software that you want to use in that experiment, and then you hand it off to Ramble and it does stuff with it. So then Ramble takes all of those things, brings them together in a workspace usually, and can do things like creating experiment directories, installing software for you, downloading input files, and piecing them together into the experiments. Then it can manage running them for you. And then once they're done, it can extract figures of merit from each of the experiments. And it will track those in a results file, and there's a bunch of things you can do with it as well. Here's a little bit more about the different components that are in Ramble. On the left are object definitions. I talked a little bit about some of them. There's applications. Those include things like executables, which are commands that you run, input files, software like a default software that you know works, software stack that you know works for this application, and then users can tweak it if they want to. Workloads, which are combinations of executables and input files. It's like something that you actually want to create an experiment out of. Figures of merit, which are things that you want to analyze. And then we have other object definitions, which I'll get into a little bit more later, but they include things like package managers, workflow managers, and modifiers. And these can exist in both public or private repositories that you have to connect your own proprietary or non-shareable definitions into Ramble, just like you could do in SPAC. In the middle is the workspace. That's the main thing that you interact with. You write a YAML file, it describes what you want to do, and then Ramble tries to do that for you. And then on the right, each individual experiment has its own execution directory, which is where its inputs and outputs live. So you can go and poke around at it if you need to do debugging or anything. If like one of your runs failed and you want more information, you can go in there and poke around at all of the artifacts. In addition to all of that, in the workspace, you can configure a software stack, because it's not super interesting to just run a benchmark if you can't tweak the software and see what other things you can do to improve the performance. So you can either connect it to a predefined software stack, which is kind of something that we're doing with Benchpark right now. We have the systems classes in Benchpark that configure software on the system already. That's the predefined software stack portion. And then you can layer on top of that parameterized software stacks that extend that to be more like applications or benchmarks that you want to run. In this, you can either connect to the pre-installed software directly if you have everything that you need. You can connect to manually installed things and not use a package manager at all, or you can drive creation of a modified software stack using something like SPAC, pip, or easy, or you can use environment modules where Ramble will construct a bunch of module load commands to load the correct modules for your system. And then from that, you can parameterize a bunch of parts of the software stack, so Ramble can generate experiments from each of those. And anyway, it can make use of the underlying package managers in other ways as well. Okay, so now we're going to talk about how Ramble works. This is going to be the workflow that we're going to go through just in steps. This is generally, if you're using Ramble directly, this is the workflow that you would follow. On the left, you create a workspace, which Benchpark did for you. You would configure a workspace, which again, Benchpark did for you because it pieced together things that it knows it needs from the system and the experiment definition that exists in Benchpark into a workspace. Then you run workspace setup, which is what you did by hand, and that actually has Ramble do things. It'll install software, download inputs, and create all the experiment directories. Then you execute the experiments that exist in that workspace. And then after they're done, you can analyze them. So we'll go through this really quick. I already told you what a workspace has in it, but this is the directory structure on the right in that gray box. You can see that you'll have a configs directory. In that, there's a ramble.yaml. That is the YAML file that describes the experiments that the workspace contains. There's also this execute experiment.tpl script. .tpl is the extension that Ramble uses for template files. If you were to open that file up, it looks like bash, but it has this kind of format that is a Ramble template file where curly braces refer to things that Ramble will expand into. So it will use that to render bash execution scripts for each of the individual experiments. After you run setup, stuff will happen to this. Sorry, it doesn't tell you, but the inputs and the software directories will get filled in. We'll go through that, I think, when we get to workspace setup. And there will be more experiment directories under that red experiments directory. In configuring the workspace, you write a YAML file. It looks something like this. This has a lot of information on it, but it's mostly showing you a lot of different things that you can do with Ramble. So there's this applications block, which is the place where you describe the experiments that you want. And it has this hierarchy of application name here, Wharf v3. Inside it, you can have any number of static keys, like predefined key names here, like variables. So you can define variables that are going to apply to every workload or every workload and experiment that exists within this application. And then there's a structure to this where you can do the same thing at lower levels too. You can define in ranks. Here you can see that the number of ranks we're going to use is processes per node times in nodes. Ramble will parameterize both of those based on the experiment definition and then execute the math to create an integer for this instead of having that be a string that you use. In this example here, I'm describing a scaling study from 1 to 32 nodes of this CONUS 2.5 kilometer workload here that comes from the application definition for Wharf v3. And then I'm going to execute that scaling study on 2 different hardware types. So here I've defined a partition that's called C2 and a partition that's called C2D. And then they have different processes per nodes because they have different numbers of cores. I will construct 12 experiments for each of those, 6 for each platform, 12 when I consider the 2 different platforms. And that is done through this matrix command here. I extract this in nodes and consume it. And then Ramble will implicitly, you can make it explicit if you want to, but implicitly zip processes per node and partition. So these are effectively 1 vector of length 2. Even though it's 2 vectors, they just have 2 names for the entries in the vector. And then up here, I have in repeats set to 5. So this will actually result in 60 experiments because it will do 5 repeats of every node count on every platform that I'm trying to run on. And then when you run analyze at the end, you'll get statistical information about each of the series of repeats that were done. In addition, when you're configuring the workspace, you can write template files. This is what I was talking about earlier, where on the left, that is the example template file that you would have seen if you looked at it. And then the command in curly braces is what will be expanded into a specific experiment's execution script. On the right, there's an example. And you can construct these however you want to if you want to write more complicated template scripts.
Doug, there is a question.
Yes.
So Parksheet is asking, one of the nice things about SPAC is that preserves its inputs in the hidden.spac directory in the package install directory. Does Ramble do that too?
Yeah, so when using SPAC, everything will be installed into your SPAC install directory through Ramble. It won't install it into the environment you get. It will get symlinked into it. For inputs, they get downloaded into a similar like cache directory that's in something like ~/.ramble by default, and you can configure where that path is, and then they will be expanded into, like if it's a tar that you downloaded, the tar will exist there, but then it will be expanded and untarred into the workspace itself. And there's an inputs directory where they exist. So if you don't want to download them again, you could just leave that there. And when you run workspace setup, it won't re-download and re-expand it. If you purge it, then it will re-download it, and not re-download, it will re-expand it because it's already downloaded.
Right, and so the other question was for, so basically the inputs and the outputs are saved for provenance.
Yeah, so the outputs exist in the experiment directories, and I think we'll talk about this a little bit. Making sure that they are preserved for provenance purposes is kind of up to the user, but Ramble gives you a way to do that. You can create an archive of workspaces after you're, like at any point, honestly, in setting up, executing, analyzing, whatever. You can archive your workspace and put it into a tarball that you can share with other people. And that can be useful both for maintaining the outputs for provenance, or even just like sharing with somebody to debug issues that you have in your workspace. It'll contain the logs. It tends to be a lightweight one. So if you have, let's say like 100 gig output file that each experiment generates, Ramble by default does not pull those in. You have to tell Ramble through the application definitions or the object definitions that we discussed earlier, what files are important to include in an archive for provenance purposes. So every application definition can have different files that it would say, hey, please archive this. And then if you wanted it to archive a 100 gig output file, you could put that in the as something that you include into the archive.
Yep. And so I will add to that. So you're probably picking up on the theme here. It's a tool trifecta, right? So Ramble is keeping everything that SPAC gives you, right? And we're keeping everything that SPAC and Ramble gives you in Benchpark. So similarly, there's a way to archive it. Additionally, the way when you just ran the Benchpark, well, when you turned on Caliper to measure things, and then you ran the Benchpark analyze command, those labels on that table, that data is present in your performance data as well. That is how we are doing that, right? Each data, it has its corresponding metadata associated with it. Each run does, right? And that's what's enabling us to then generate the scaling study over, you know, the figures you were looking for from the scaling study, right? None of that was manually entered. That is a, you know, we know what the problem size is. We know how many resources you were using. All of that information is in that as well. So if you only wanted to share the performance data was that provenance and not necessarily, you know, the entire workspace, that is doable as well. So we are essentially kind of thinking of this as, there might be different reasons you are archiving your stuff, right? You might be just archiving for what ran, what failed, that might require logs. You might be archiving just the performance results along with all of the versions of the software and all of the parameters. Depending on what you do, you can choose which data to archive and share. But all of it exists. That's the whole point. Full provenance is the whole point. And full reproducibility, we take it. Well, my next slides will show you how we basically tackle that from the command line basis in order to generate the same experiments. So I'll hand it back to Doug.
Okay. So then after you finish configuring the workspace, you can set up the workspace. Here, I've said this a couple times, but it'll execute a bunch of phases for the setup. The phases are determined by the objects that build up the experiment. That's a lot of the internals in Ramble. But to begin with, we would download input files. So this will figure out what input files you need for the experiments and then download them. It will expand them into this inputs directory and then define variables so that each experiment can connect to the path where that will exist after the expansion is done. It'll execute software phases, which will install compilers. It'll also install whatever application files you need. I probably need to remove this SPAC applications reference because that doesn't exist anymore. And it will construct a SPAC environment for each of the individual unique SPAC environments that your experiments need. It will also construct variables that tell each experiment where the installation directory is for relevant packages in the SPAC environment. So you can do something like get the binary path out and refer to that in the application definition that you write. And then it will also create experiment directories. And like I said earlier, it'll render every .tpl that's from the configs directory into the experiment directories. You can see on the left now, after you've run setup, this is expanded into a lot of other things based on that config that I had earlier shown you. Once setup is complete, you can now run the experiments. There are multiple ways for you to run them. You can run them by either just executing this all experiment script that exists in the workspace root, or you can run Ramble on. Ramble on is more featureful in terms of what it lets you do. By default, it'll execute a specific entry in the workspace that's called batch submit, which is like a templatized string that it'll execute as bash, but you can pass in arbitrary things as well for it to execute. You could have it run like something to get additional information out of every experiment through custom executors in Ramble on. After they're all, so how they execute depends on that batch submit command and how you've built up the experiments. You could either have them run sequentially by running the all experiments file, depending on how you built batch submit up, or you can run them in parallel by submitting them to a workload manager, as you did in that first demo where you submitted them to Flux and then it handled running them on different nodes. After they're all done, there are ways through Ramble's workflow managers for you to have Ramble like block until the experiments are complete. But if you don't do that, then you just wait until all of the experiments you want are done. And once they are done, you can extract the figures of merit using Workspace Analyze. Here, you will by default be given a results.txt file. It will have a summary of the figures of merit that were extracted with their units and things like that. It'll give you, assuming you used SPAC, a pretty detailed description of the SPAC environment that was used for the experiment. It'll have like every package and version. And it'll include other things too, like if a success criteria failed, which one failed, so that you know like why your experiment failed or why it worked, but they'll just have paths if they worked. You can also get more detailed formats through YAML and JSON, and those will have even more information. In the YAML and JSON formats for SPAC specifically, it'll include things like the compiler that was used, the version of the compiler, and the full variant string for the package that was installed, so that you have extra provenance information to understand and reproduce the software stack later. Okay, so we talked a lot about how you create a workspace and what things you can do with it. Some other things that you can do with it really quick, just to make sure people know this stuff. You can parameterize software definitions. So the way that you can convey the software stack that you want to use to Ramble is through the workspace configuration file. And you can parameterize any part of that, just like you could parameterize the number of nodes in the experiment. So here's an example where I'm picking different SPAC environments over here through this env name variable, and I'm parameterizing the MPI that I'm using to either be Intel MPI or Open MPI. On the right, I've constructed a templatized package environment, SPAC environment, that's Wharf MPI. It has the same name. And I'm templatizing the package MPI that I want to use. So here you could imagine that I'll get two experiments. One is Wharf IMPI and one is Wharf OMPI. Each of them has this MPI expanded to be IMPI or OMPI. And then when IMPI is used, this Intel 1 API MPI package will be used for the MPI package. And when OMPI is used, it'll be OpenMPI 4.1.4. So now I've got two different MPI software stacks that both have Wharf. So I can run these in a single workspace and compare them to see the impact of changing MPI implementations on my performance.
All right, so let's quick pause for a question. Alfred's asking about a Ramble hands-on exercise. He doesn't see a directory for Ramble in Jupyter Hub. It's there, but I'll let Doug answer that question.
Yeah, so there's a Ramble directory. I think the way that Benchpark actually pulls it down is it puts it into the workspace. So when you did Benchpark workspace init, it should have downloaded Ramble and SPAC, and you can poke into there to see Ramble specifically.
Right, and so some of the commands you were running, right? Every command that you started was Ramble, right? That was directly a Ramble command, and the Benchpark commands did a lot of this setup that Doug is showing now. This is what's happening behind the scenes for you
Yeah.
when you're using it from Benchpark. But yes, we are directly using Ramble, right?
And you can go in and see the ramble.yaml for the workspace that you've got. If you poke into that workspace directory, I think it's called WKP, in there somewhere there should be a configs directory. In the configs directory, there is a ramble.yaml. If you look at it, it'll look something like this.
Yep. So basically, we've encoded more things, right? And we are generating these instead of you needing to write in this format.
Yeah.
Yep.
And then something else that you can do with Ramble is, I mentioned these earlier, there's an object definition that's called modifiers. Modifiers allow you to abstract modifications to experiments into a separate object that you can layer on top of any experiment then. A really useful example of this is using a performance analysis tool. Here I've got Intel APS. So all I really need to do is add Intel APS here, and then it will inject the correct commands into my experiment definition, or the templatized experiment that gets rendered, to call APS while the experiment is running to collect performance data and then generate a summary at the end. It can also inject additional figures of merit. So in this case, it will have like the MPI time as a figure of merit that's tracked alongside whatever the application figures of merit were, and like the top 5 MPI functions that were called by the experiment, because those are things that Intel APS outputs now. And that, again, is independent from whatever application you're using for the experiments. So these end up being like nicely composable definitions that you can use to construct more interesting and complicated experiments down the road.
So there is another question in chat. It's a silly one, but since we're pausing here anyways, basically the question is how did Benchpark and Ramble got their names? So Benchpark is pretty simple. We wanted a place to park our benchmarks, and so that's kind of what we were riffing on. But I think Ramble's Doug's answer is much better. So I'll let him.
I don't know how much to go into my answer. Ramble was a fun conversation I had with a coworker who I can tell you more details about later, maybe ping me offline about that part. But it's effectively named after Led Zeppelin's song, Ramble On. And we had a fun conversation around it. And it was almost like a challenge to name something Ramble. But it ends up being a backronym as well, which I don't use all that often, but it stands for Reproducible and Measurable Benchmarking in a Layered Environment.
All right. I think we can pause here for a second and see if there's other questions for Doug. He's not going to disappear, but we're going to switch back to Benchpark. So any questions?
In Ramble's docs, which I can send a link to, I think it's also in the HPCIC tutorial links at the very beginning. We have a lot of tutorials for various things that you can do in Ramble. So you can always go through those if that is interesting to you. And I'll add a link to them in just a second.
Yep. So Doug has a lot of material as well on his docs. We basically have made a very, very strong effort to, similarly, the way that the Doug is using SPAC without re-implementing it. We're using Ramble without re-implementing it, right? We're just layering on top of it. And so going back to an earlier question of why we developed this tool, right? So partly, right, you have to realize that once we found SPAC and Ramble, we knew most of the components we wanted were there, right? And so we only wanted to add what we needed for the purpose of our jobs, right? And so I can essentially give you a tiny little overview of what that looks like. We find ourselves needing to repeat experiments, replicate experiments, and reproduce experiments. And so the hands-on will be, well, this is the link to hands-on, but we don't need to go there yet. Am I on the wrong slide? I should be on slide 50.
That's the first one.
Okay, I just went to a random page, I think. Okay, why did it go there? I don't know. Okay, and so these were our goals to, these are the types of things we do for our data center, that for procurement, for acceptance, for all of these things. And so what do we mean by that? And so repeating an experiment is, we need to verify that the application still builds and runs. We need to hand over the task from one teammate to another. We need to figure out, how the benchmark's performing as the system ages. Or we might just be running many trials of the benchmark to study the noise on the system and so on. And so effectively, our definition here is the hardware is the same, the system software stack is the same, and we're running the same application or benchmark. Another use case is we need to replicate this experiment, and by that we mean, we need to verify. We got a new version of ROCm, which we get, very, very frequently, new versions of software, right, for our systems as fixes, bug fixes go in, or performance improvements go into these to the software stack. And so we need to verify that that new drop of software we just got still lets us build the benchmark. The benchmark still runs with this. We want to usually compare the performance, make sure it's not a performance regression, right? And we want to evaluate the performance of these different substitutes, right? So the day that I get a new ROCm, I might kick off a run with the ROCm that's stable on my system plus the new one that I got, and I might be comparing what that looks like. And then, of course, there's a million other experiments. Do I really want to pay for the Cray compiler, or is GCC or GCC or Clang giving me the same performance, right? Those kinds of comparisons, or different MPI versions. Open MPI versus Cray MPI, all sorts of things like that. And so essentially what I'm saying is I'm still running on the same machine. It's still El Capitan, but I might be playing with my software, right? I might be comparing different ROCm versions, different MPIs. But ultimately, I do want to run the exact same benchmark on top of that, right? I want to make sure that I am running the exact experiment just with, this one thing that I wanted to evaluate the difference, just with that one thing differently. And reproducing, by that we mean running on a different system. So of course, there's always going to be comparison between different hardware, just trying to figure out, do we perform as as good or better on this GPU versus this other GPU, and so on, right? There is a myriad things we're looking at. So we want to be able to build on both systems. Or all systems of interest, right? We want to be able to run there quickly. We want to be able to still run the same apples to apples comparison, right? So we still want to understand that we're running the same benchmark in the same way as appropriate. But how does it perform across different hardware? And essentially that gives us a lot of information of how our workload behaves on different types of hardware, and which kind of hardware is better for our workloads, and so on. Enables a lot of choices and decisions for our data center. And so formally, right, so I said repeating was all three were the same. Replicating was the software stack was slightly different. When I'm talking about reproducing an experiment on different hardware, clearly it's going to have a different software stack. And the application is approximately the same, right? If I am moving from AMD GPUs to NVIDIA GPUs, I still want to make sure that application functionally does the same thing. However, somewhere in there, one of those has got to be mapping to ROCm, and one of those has got to be mapping to CUDA. And so that's the difference that I am going to have, because you've got to map onto your hardware. But the rest of it, right, I need to be able to be sure that it's an apples to apples comparison. Okay, and so how do we do this? And so this goes back to the Benchpark specifications that we have added on top of SPAC and Ramble. Basically, we have a system specification that I've showed a little bit. That's both the software stack and the hardware specification. I am not going to go into this. We will, however, go into how to write an experiment.py in a moment here in our next hands-on. What it's going to use, right, it's just going to directly use a package.py for your benchmark, right? So for the purpose of this exercise, we'll grab one that already has a package.py, the spec package written for it. It will also directly use an application.py out of Ramble. Right, so we will basically we will work with one where the application.py exists. And essentially what we're going to encapsulate in this experiment is essentially the directions on how to be then mapping onto the system, how to do different types of scaling, those sorts of things, right? And it's going to enable all of these in the following way. So sorry, this is a busy slide, but I thought it was useful to kind of have them here for comparison. So the repeating is the first, essentially the two versions of the experiments here. For application, it's the two middle ones, and for reproducing, it's the bottom row. So remember, for repeating, everything needs to be the same. So for this purpose of this example, my users are different, right? User 1 here and user 2. They're using the same commands. They initialize their system the same way, right? They both essentially grabbed the same system A with the same parameterization. They both initialized their experiment, which in this case is Quicksilver with OpenMP and the weak scaling. And basically they've set up this experiment, and from there you go into the Ramble commands to actually build it, and call spec to build it, and to actually run it. So they did everything identically. The output better be identical or close to it, right? There's modulo system noise, right? But if you are doing this on the same day where the software stack is the same and it's all possible, then we actually have utilities to then compare that those two builds were indeed the same, that everything was run in the same way, and then of course the tooling to compare that performance. You know, if you see some noise, you might want to have user 1 and user 2 run 10 times and average it somehow to kind of convince yourself that indeed that performance is the same or not. If it really is different, I'll show you in a minute how to look at that. So that's to repeat an experiment. To replicate an experiment, basically, you know, the same thing, right? We said that it's going to be the same physical machine, the same hardware. The software stack has moved on a little bit, right? So there is now 2 different compilers that I am wanting to compare, and then other than that, I want to compare the same benchmark. So in this case, you know, either user 1 does both things, or user 1 does the thing on the left and user 2 does the thing on the right, doesn't matter. The system is initialized, and so what I am going to say, you know, I'm picking my Intel cluster, and I'm going to in one experiment, I'm going to pick a compiler to be one version of GCC, and then in another one is another version of GCC. Whether it's, you know, different versions of GCC or just different installs of GCC, right? If the sysadmin is playing with updating installs, they can use that as well. And so, but then the benchmark experiment is actually initialized identically, right? So I am not changing anything about my benchmark. And then I generate my workspace called Ramble commands. And now I am going to be able to, again, I'm going to be able to see what exact differences there are. So, and I better see that this is the 2 different GCCs that I am using here, and that's the only difference, right? And then I'm going to be able to compare the performance as well, so that I can see if there is a performance implication from using one GCC versus the other, and I'll show that in a second. And then the reproduction here, we talked about different system, right? Different system, different software stack. The application may needs to target a different programming model or something. So indeed, right, basically this is a different system initialized. This is an Intel cluster and the other one is IBM cluster. In this case, I am going to be initializing the experiment differently as well. So Quicksilver is initialized with OpenMP for the Intel cluster because that's a CPU-only cluster. My IBM cluster is actually soon to be retired, sadly, Sierra. So this has NVIDIA Voltas on it, and I want to run with CUDA on those on that system, right? So I'm going to basically say I want the CUDA version of Quicksilver, and both of them will do the same kind of scaling, so we can compare those, right? And basically, again, I am setting up, and I use my definition of experiment in the system, and off I go. Those are the 3 things, right? Those are the 3 kind of main use cases that we've talked about. And so then from there, we can go back to our analysis of performance. So as I said, there's scripts, there's functionality to compare the builds and all of that, and you can find that in the docs of how we do that. Here, I just wanted to show a quick study. So basically, we had a student who was comparing, you know, he built a compiler and he was comparing that to the so that he's calling that self-installed compiler. This is an undergrad, by the way, did this study. He installed a compiler and he wanted to compare that to the compiler that's already installed on the system. And so basically he was okay, so for self-installed compiler, he wanted to see if there is much variance. So he ran a bunch of examples and essentially was looking, you know, is there much spread between in the performance on these examples? here he ran one version of this was his own, the compiler he installed, and another compiler that was on the system. They were slightly different versions. I wish this didn't pop up. How do I? Okay, there we go. So there were slightly different by a minor version GCCs, and so this is what he was looking at. On the same system, right? This is both on the Ruby system that he did both of those experiments, and they look kind of the same, right? Then he looked at two more systems. So he looked on Sierra, which is our soon-to-be former flagship machine, and he also looked at Dane, which is another CPU-only cluster at Livermore. And he started looking at this. He's like, oh, these look close. These look also kind of close. These look kind of far. What's going on? So he did a little bit of a, statistical significance study on these numbers. And basically, the p-value told him that on Ruby and Sierra, the differences are indeed not statistically significant, but on Dane, they are statistically significant. And so he wanted to dive into that and figure out why that is. And so outputting the results, the performance measurements, there's more functionality in the Thickets tool that this is output from for comparing across different machines. But essentially, we could very quickly programmatically confirm that all the green numbers are the same, but this kernel here is basically where all of the difference is coming from between the runtimes of those two runs. And so we narrowed it down and figured out from there why that performance was different. But essentially, this is an undergrad, over a course of a couple of weeks, getting to, learning about HPC enough with these tools in hand to be able to get to actually analyze performance and actually be looking at what's going on the systems. And so, essentially what we have enabled is a way to do these different types of studies, which we do for many purposes at our data center. We sometimes need to repeat experiments, sometimes replicate, sometimes reproduce. And so basically, we've been able to do this. You can do various portions of this, with different users, with different systems, whatever it is that you're trying to do. And you do get a full record of the specification, how you specified it, what ended up getting concretized and run on your system, and the measurements to go with it, with all of that metadata. So that gives you the introspection and reproducibility. So at this point, I can take some questions, but basically we're going to be gearing up to do a second hands-on portion here. So basically, we're not showing you how to add a system description. That there is documents on that. We're also always happy to help if you are attempting to do this and have any questions. But we wanted to talk about how to add an experiment. And so essentially what we're going to be starting with is an experiment that exists, but you're basically going to be writing that experiment so that you can you can understand where the different portions of this are coming from. Let's see. So we specifically wanted to make sure that there is already a SPAC package.py, because if we were to teach you how to use SPAC first, we would never get to Benchpark. Similarly, there is an application.py that already exists for this, and that's coming from Ramble. You can also see them in the Benchpark repo. Benchpark repo, by the way, is well, okay, you don't see them in here. If you do, that means there is a version that overwrites what exists in upstream SPAC or Ramble. you can use that kind of as your workspace while you get things working, and then upstream those files to SPAC and Ramble. We don't need ownership over the SPAC packages or the application.py. Those belong in those repos in SPAC and Ramble longer term, but we enabled kind of a temporary while you get things working space, so that you can get all of the components working together and then upstream the versions instead of waiting for pull requests to be merged and so on. Okay, and so what we're going to be doing is, let's see, so, okay, so in Benchpark, right, I'm in the Benchpark directory now. There is, so here's actually, let me show you really quickly the repo. So in the repo, right, you do see various various experiments that we're sort of have something in flight, but it hasn't been upstreamed yet, right? HPL is not, oh, it is here. Why? Oh, I guess they both are here. I would have to go, we actually have scripting to figure out if they're the same or if there's something that we've changed that we then need to upstream at some point. But this is where you would find those. If they don't exist here, then we absolutely are just using the ones from upstream SPAC and Ramble, which both of those, as Doug said earlier, those get downloaded when we basically do Benchpark workspace setup. So you get a full clone of SPAC and Ramble. But welcome to modify things here if you need. It's also can be handy to take a look, essentially look at your application.py as you are writing your experiment, because those are the parameters you're trying to specify. Okay, so I'm going back to the Benchpark directory. And so in here, you'll see there is a systems directory, right? And this is the different systems in here. So if you wanted to see basically how one of the systems looks like, you can basically go see LNL, El Capitan. Right, so here's the system.py for that. And so everything that we've got is up here, right? The software stack, all the things are in here. Okay, and similarly, there is an experiments directory, right? And then basically, if there isn't already an experiment in here, you would go ahead. Why does it do that? If there isn't an experiment in here, was that name, you can go ahead and create a directory in here. HPL already exists, right? So we're creating an existing one. And so basically, let's see. What was I going to say? Oh, I did want to mention, because the SPAC, Ramble, and Benchpark projects all work very tightly together, very closely knit projects. We do try to essentially keep the naming as much as possible, the same, right? So if there is a package.py for HPL, then there should be an application.py for HPL, and the directory in Benchpark experiments should also be named HPL. That just makes things less confusing, makes it very directly obvious that those are all specifications for the same thing, just at different levels. But yeah, we do accept submissions this way, right? So if you put a PR, a pull request, we're happy to take a look and see at what you have written, what you're trying to contribute. So, but this is how you would do that. And so basically here, the experiment.py already exists in HPL. But essentially this tutorial is walking you through how to write one. So if you wanted to move this one, the existing one, experiment.py, to hide the file or rename it something, and create a new one, then you could do that. Okay. All right. And so, of course, you would be starting essentially with these instructions here. We do have to import some things, right? So day one, we're probably going to be writing an experiment, let's say, and we're going to know that it's going to be an MPI experiment right away. So for HPL package, right, and we've linked it for you here. This just points at the code in Benchpark repo, or you could be looking at the package in the in spec proper as well, if that's where it lives. But you can basically, let's see. So here you see that there's OpenMP. Oh, that's why we have a copy. We wrote a caliper version, and HPL sadly is distributed as a tarball, and so we haven't yet given back the caliper instrumented version. And so basically this package enables a plus caliper option, right? So we're gonna, it's gonna do all of the machinery for building with and linking to caliper. If you essentially say, give me HPL plus caliper. So that's why we have this package, but basically the rest of it is the same as in upstream spec. But until that source code, until that tarball contains caliper, that wouldn't work, right? So for the caliper version, we're using David Buma, who's the author of caliper, wrote an HPL caliper version that's sitting in his own repo here. It's public though, so we can get at it. Okay, so any questions on that? Does that make sense? That we can see there's OpenMP and there's caliper variants, so we can then you could confirm with the source code what exactly that does, or you could go with this and basically see the output once you actually get it running and see how much of a caliper instrumentation there is, right? Is it 2 regions that are instrumented? Is it a lot of instrumentation, right? At this point, you don't know, but you do know that the package is set up to work with caliper. And so basically what we're going to do, what that means is we can essentially say, all right, we said experiment and MPI only, but we can also add, basically add an OpenMP experiment and a caliper experiment because that exists, right? And so for that, you've got some imports to do, and you've got some more base classes to derive from. So essentially these base classes is what already is, there's no reason for everybody to indicate how to pass on those parameters to spec and Ramble. We've done it in the base classes because, how to do that looks the same every time. Okay. And then you can start adding variants and maintainers. So just like you have in Spec and Ramble, you've got maintainers for their classes. Here we can also indicate who's the maintainer here, and then variants provide configurability for Spec and Ramble downstream. So what we're going to do here is we're going to add a variant for workloads, right? And so there is basically the, let's see, package.py. There's not a link to Ramble experiment, but it's basically, there is one in here. But it also inherits from a couple of things, right? And so not a lot is in here. In fact, we are just, we're only inheriting so that we can add these tags. And actually, what we're in reality, what we're using, right, is the built-in from the Ramble application. Let me see really quick if there is a link to that. There it is. We should have moved it higher. Sorry about that. But basically, so this is the one in Benchpark repo. We just added tags for our own purposes. But then the one that you are really looking at is and this is in Ramble, and Doug has the how-tos for how to write this application.py in his documentation as well. But basically, there's different workloads and different workload variables that we are that we want to set values for. So we are going to start by saying, all right, we want to grab a couple of variants. We want a standard workload, right? So one of the workloads, or was it? One of the workloads was standard, right? So we're just grabbing one of them for right now. Okay. And then another thing that we're going to do, because, no, I'm going to have to go back to my package deploy. Because I want to use this version from the SPAC package, right? Because that's the only one that I have instrumented with Caliper. I'm going to add myself a version that basically this 2.3 caliper, and that's just going to point at that specific version in that SPAC package, and that way we can so by default, right, we can use that. We can also use those other specifications, right, that might be existing upstream. You know, the 2.3 without the dash caliper is just a regular 2.3 version of HPL as you would find it, you know, basically here, right, where the SPAC package is pointing at it. Any questions so far? Okay, and I guess we're making David the maintainer. Okay, let's see. So once you have done that, those are your variants. You have essentially enabled yourself to use different workloads from the application.py, different versions from the package.py. Then you need to write an application section. So this is what then builds the YAML files that Doug was showing. And so we essentially have this compute application section function in the base class. That's why we imported this experiment up here. And so that enables us to define experiment variables and scaling configurations. And so, experiment variables are here, right? So the different workload variables that are defined in the application.py in Ramble, right? We are gonna basically make some choices out of this. Essentially, we can define what the n is, which is the size, and the different levels of the grids. You know, how to essentially target all of these runtime parameters. So the number of problem sizes, the problem sizes, and so on. Right. So we're just going to define those. So basically, we have gone so far to this point, and now we're gonna essentially define this define compute application section. Okay, so basically, the execution mode is another thing that we have in Benchpark. For testing purposes, for like CI, we try to define really small problems, and that's actually what we're doing today right now, because we can only give you guys a node each. So that's a small problem on the HPC scale. So that's what this means. We're basically saying, all right, our number of nodes is going to be 1. But this portion here basically lets us then also have orthogonal definitions, right, for bigger problems that we might want to run when we're actually looking at performance. And then we're just gonna say we have to have all of these experiment values, right? We're gonna go and pick the size of the problem, the number, the number of them, and so on. And so it's really overriding this, basically in this file, it's going to give Doug the values, give Ramble the values for these variables that are defined in application.py. Okay. And so otherwise, we might set some other values, right? For other problems that are not, let's say, not this test for one node. Okay. And then we're going to get to the definition of how to work with our system.py. So basically, we're going to want to use the cores per node on this node, right? So that's going to be our number of ranks. Where your system definition, right, like I was showing in El Capitan as an example, your system.py knows how many cores there are, right, on that specific system. So when you go to instantiate this experiment for that system, you will have the number of ranks, will be calculated from there. You will probably also want to define, depending on what your application is, right? If this is you're working with OpenMP, you're going to want to define threading and so on. And then basically, these are the variables that are required for the experiment. You've got to tell it how many resources to use, right? What the problem size is, right? So that's calculated from these variables here, and then what the total problem size is. Okay, so that's for one run, right? We've defined how many ranks we want. We've defined the problem size. We've defined, what parameters should be for one. For one execution of this benchmark. There's, of course, more. So this is a link for more information for when you're making something more complex. Okay, but then we did want to get to at least show you a little bit of how you define a scaling experiment. So in the compute application section, we would then import a scaling module, right? And we would add some information on how we want this application scaled. So we have already done this. We need to add the scaling mode, and somehow I missed the maintainers. We will need it, otherwise it's gonna say it doesn't know what that is. Okay, so maintainers and adding the scaling mode. Okay, so we're going to want to scale. The other thing we are adding is basically we're going to say that we want to strong scale and weak scale. And so we will derive from those classes, which will then require for us to define a couple of things in order for Benchpark to know how you want that problem scaled. Okay. And so then we go back to our compute application section, and we'll just go to the bottom of it. And add this strong scaling definition and weak scaling definition. So what it is, this takes a little bit of staring at. We'll see if we can improve the on what this looks like. But essentially, what we're scaling is for strong scaling, right? The number of nodes the application is going to be using is going to be growing. So it's going to be the number of nodes times a scaling factor every time you double your resources. For the problem size, though, we're going to keep it the same. So we're not adding, we're just saying it's just the same value. For the weak scaling, though, we're basically saying the end nodes, we are going to increase that times the scaling factor, which is usually 2. It becomes a parameter on your command line for you. But then for the problem size, unlike in strong scaling where you're keeping it the same, for the problem size, you're also going to be growing it by the scaling factor. And the reason we have it like this is we do have some workloads where you need to indicate scaling in 3 dimensions, or the growing of the problem size in 3 dimensions, like Kripke, which I was showing earlier. And so we wanted a way to be able to indicate, which variables, right? And so for Kripke, we would basically be indicating there's 3 dimensions, and you need to work with all 3 dimensions. And by the way, you need to increase the decomposition, right, for the number of nodes, the same way that if you're growing the problem in this dimension, you need to add more processes in this dimension as well. So we do have the flexibility to work with 3-dimensional simulation-like things, which is actually a lot of our workloads. So that was an important use case for us. And so there's more information on that if you're interested in that. That's a bit more code. Not a lot. Okay. And so this actually takes care of the interface with the Ramble itself, right? We have defined, which workload. Basically, this gives us now the full interface for the what's defined with application.py, and so it can work with Ramble's application.py. Next, what we're going to do is we're going to basically add a similar section for the package.py, right? So for the build information, how to interface with the package.py. Let's see, do we need to add anything here? I think we're good. Nothing to change here. Oh, okay. And so basically the compute application section is what we were just working on. And the compute package section will go basically after it. Okay. Well, turns out we actually don't need to do a lot. We have specified the versions here, right? And so we're gonna grab the version from so okay, on the command line, the user will say HPL with such and such version. And we are just gonna grab that version to point at the correct, to point at the correct, wrong window, to point at the correct version here in the SPAC package. So that's all this section is going to do, because essentially we're by inheriting from OpenMP, if you say HPL plus OpenMP, this inheritance class will basically pass that plus OpenMP to SPAC. to build the benchmark correctly in any other flags. And so this version is the remaining piece that we needed to grab from the user and pass on to the SPAC to SPAC in order to build this. Any questions so far?
Nope.
All right. Okay. And so basically, once you've written this, and so we are at just about 100 lines here, right? And in order to validate this experiment, basically, we've already initialized the system, so you shouldn't have to do that again. But let's see. I wonder if I can. Nope. I'll have to get out of this directory.
Here's a
But
question if you want to take it.
yep, let's do
If
it.
you have so the question is, if I had a cluster with mixed node types, would I need to create a separate system for each node type, i.e. some nodes have just CPU and some have PCIe GPUs?
So you have some choices. You could write your system, you could write it as two variants of the same system. It will probably be easier as defining it as two separate systems, system A, system B. I actually think that, well, maybe I can do this here. Let's see. I think we might have a system like this on the list. Yeah. Well, no, not that one. So it depends on how different they are, right? So we do have LNL cluster system.py is used for a number of our clusters that are CPUs. They're not identical. So the CPUs are slightly different, but the software is installed the same way for both. So in fact, it's shared. It's on the shared file system between, let's say, these two systems. There's others on this list like that. There's Dane. And so we've chosen to define them as variants of the same system.py, which is just called LNL cluster. If you're talking about the CPU and a GPU partition, it might be easier to define it as a separate one if there's different software stack that you're dealing with. You could define it as two separate ones and then see if you could always combine them later if you wanted to. I think Jules is actually so the Ulick machine as the one I was looking for, but I think I only have the booster partition of it here. I guess we may have not upstreamed the other one. The other ones may still be in the PR. But basically, they have a system that's like that has different partitions. And so in it, right, you would have to define the different software stack is going to matter. If there is a you need to indicate, how does this work with your queuing system, right? If you basically have to submit to queue-GPU in order to request the GPU partition of it, right? That would need to be reflected in that system.py. Again, you could try it as two variants of the same machine or two separate system.py.
With there's a follow-on for that question, and then there's one other question too, which I can ask you. But for the follow-on, the question is, does the separate system, or sorry, does the variance of the systems in a single system.py also work if the CPU types are different within the partitions, like
So
different core counts, different memory size, and everything?
Right. So you can specify that. Okay, let me just. Let me go to this here. All right, so you can go look for any examples of these things, right? But basically the what I was just showing is right here, right? And so Ruby, Magma, and Dane are slightly different, right? They've got different cores, different types of cores. We even go into details like some of the cores are reserved for the OS, if that is the case for a specific system. We do have essentially the queues, what kinds of queues there are. Sorry, close things for me. If you have different queues for those machines, right? How submission would work. Let's see. So for the CPUs, we haven't had to pass on the microarchitecture because that's still well, it's not being cross-compiled. So SPAC is still able to grab all of that as normal. But does that answer your question? So
Yes.
that's one way to do it. What I'm saying was, so this is the only differences there were for these are all CPU only clusters, and so we literally have a variant that says one of these, right? Which one, and then you key into this table here for your resources. For the CPU only versus CPU plus GPU, there's going to be more differences because you're going to have an additional piece of your software stack for your software stack, right? For the GPUs, right? And so that's gonna be different, right? And so because I've kept this to CPU only, I can basically say these are, we can only do OpenMP and we can only do MPI on these machines, which by default we assume MPI actually. But if you were to write it in terms of, this partition does this, then it would have to be, an OpenMP partition for CPU only, and then it would have to be a CUDA or ROCm partition for the other half, right? So that's going to become pretty complicated pretty quickly. So I would say, limiting to systems that are fairly similar and particularly share the software stack, absolutely make those as variants on the same system definition. When you're going to start talking about a CPU partition and a GPU partition, I'd probably start by defining them as separate systems. A separate system.py, right?
Okay, that's it for all the questions.
Okay, so was there another one?
No, the other one got answered in chat.
Okay, cool. All right. But yeah, basically, you're welcome. So this table is here, it's generated from these files, right? And so, but the actual specifications, what you see is what you get, right? All the systems are defined here. All the experiments we've got, you have every definition right in here that we have basically, right? As soon as things are merged, voila, there they are. Okay, where was I? Okay, and so basically, at this point, we have written this class, and so this experiment.py, and so what we can do is we would then go back to our Benchpark directory, right? And since we've already initialized the system, I guess it was a while back. Right, we've already initialized the system. You shouldn't have to do it again, but you can. Actually, no, you can't. It's gonna complain because it's already there. Yeah, it's complaining that the directory already exists, right? So if I removed it, I could initialize it again. But essentially, let's just use the same system that we have already initialized and essentially initialize the Benchpark experiment in it. What did I call my system? HPC tutorial. All right. right? So this is what we're calling it. This is what it's called. The directory is called in the experiments directory. And it did not complain. And so basically from that point, you can go on to testing and essentially go through the first, the previous tutorial, right, for how to then basically, so we've gotten you through, so we've initialized this step. We've gotten through step 4 of the first tutorial we went through, right, and then from there you can go for Benchpark setup and move on to the Ramble commands to set up Ramble workspace and Ramble on to run. And the whole reason we wanted to grab the caliper version, right? If you grab the caliper version, then you can move on with this benchmark analyze and get to this point. So actually, we didn't do that. Let me start. Let me redo this step then. So if I wanted to do benchmark analyze, I needed to add these parameters, right, which we did describe. So let me see. Yeah. So I'll just remove the HPL experiment and I will initialize it again. So I will say HPL plus strong plus and caliper is equal to time, comma, MPI. Okay, and then I can follow the benchmark setup. And so you guys are welcome to stay on and do that, but I did want to see if there is further questions that you have. There's more. The experiment appendix is more on inherited experiments, right? Once you kind of get to more complex kinds of scaling, there's more things you might be wanting to do. You can add on more experiment variables. Let's see. So this is a little example for if your scaling was a three-dimensional, if your benchmark is a three-dimensional space and you gotta grow the different dimensions separately. So there's some examples on that. And you can also basically go through this. And so what it's going to generate is for Ramble, right, is these matrices that I think Doug showed for what you can work with for the different types of experiments as well. So anyways, more material available. Happy to answer any questions. The other thing to check, right, since we did write an experiment.py that exists, you could compare what I was trying to do, but it didn't let me diff very easily in that GUI. What I was trying to do is compare the experiment.py I wrote for HPL versus the one that we already have, right, which is getting tested and it's getting run, so we know it runs. So that's another thing to compare, right, for some guardrails here. So let's give it a minute and see if any of that helps. Okay, so we didn't test this with caliper without OpenMP. So that error is telling you that that's basically not a valid option on here because the concretizer is not finding the right moot library. So we would need to do plus caliper plus OpenMP. So by the way, in the software stack in the system.py definition, right? We put things in there that we want. It's optional. If you don't put libraries in there. If you don't put MPI in there, SPAC is going to proceed to build you one. So it's basically, if it's in there, it's SPAC is instructed. We essentially give SPAC instructions to use the ones that are available in that install. But then, you can run into concretization errors if something is not quite matching up. But you don't have to, right? If you can basically have, you can provide nothing, and SPAC will build it from scratch, build everything from scratch. So, yep. So, Parikshit, I appreciate that. Errors are useful, right? We stare at those all day. Because Ramble builds on SPAC and Benchpark builds on Ramble and SPAC, right? Essentially, you're gonna get 3 flavors of errors here, right? So what you're looking at is a error on SPAC concretization, but it's because of what software stack is specified for that system in Benchpark. Okay, so we didn't test. So we tested plus strong with caliper equal to time. How does the OpenMP error come up then? Parikshit, can you paste the how did you initialize your experiment? Basically the Benchpark experiment init line. Yeah. So you did a plus OpenMP, but somehow that ended up, caliper ended up without OpenMP. Okay, so basically what happened is a mismatch between the open blast version that you have and the caliper SPAC package, right? And so that's the fail to concretize is a SPAC error because those two are incompatible, because apparently the HPL 2.3 plus dash caliper, so that's the handle for it, right? Plus caliper minus OpenMP is what ends up being generated instead of plus OpenMP. Michael, is that because we don't need to indicate plus OpenMP? Just plus strong is sufficient because we are basically, the system already was initialized to work with OpenMP. Yeah, but did you have to remove the blast from your system, Michael, when you did this? Okay. Okay. So basically, the system definition as we have it is not compatible with the OpenMP version of caliper, and so you have 2 choices, Parikshit. You can build without OpenMP with the system definition that we did have. And so that would be the system that you initialized earlier in the tutorial. Or if you wanted to build it with OpenMP, you have to remove the BLAS out of the system. And so you would have to remove the directory into which the initialized system went, right? So you'd have to reinitialize the system and then reinitialize the experiment. But there's more material both on Ramble docs and on Benchpark docs and obviously SPAC docs. So sometimes it's wading through that. So we're also kind of happy. We're also happy to point you to basically, where you need to look for if you're not already familiar with SPAC, at least, right? That can be a tricky lift on its own. So the SPAC Slack that the channel is in will also has also appropriate channels for SPAC questions as well. But we're happy to point you at any resources that you might have not yet discovered.